everyone. Welcome and welcome back to our quantum computing class on Sunday. This is our 18th class, and also we had some new people come in, new communities like 10 sessions ago. But every day, every time we have new people joining us. So for anyone who missed any previous classes, don't worry, they're all recorded. They're all posted on Hackaday. The project is called Quantum Computing Through Comics. You should be able to find it on hackaday.io. And every Sunday, we spend 30 minutes to an hour, depends on one concept. And we discuss that and use the Microsoft QSharp documentation as a guide, as well as the quantum katas, which we use to do coding. And today is a continuation of last week's short class on Shor's algorithm. We're not doing any coding, but I will be directing you to some exercise that you can do afterwards. Just a quick recap of Shor's algorithm and the problem that it's trying to solve, or the problem that it will create, is that the RSA encryption scheme that we talked about last week is based on the fact that classical computers are really bad at factorizing large numbers. So our RSA encryption is trying to use a really large number and then using its factors as keys, private keys. But then because the number is really large, it's very difficult for people to break and find out what the private keys are. But then Shor's algorithm comes along that is very, very efficient to find these factorized primes of a large number. So what is relying on, as we have seen repeatedly in a lot of quantum algorithms, that is based on, again, entanglement of different states and superposition. And in this case, we also saw this new thing I introduced last week, the quantum Fourier transform. So basically, you have a really large number, which will give you some other numbers that you can use to find using Shor's algorithm, and then that breaks the encryption. So this is very dangerous. If that actually, if we build a quantum computer that's able to run Shor's algorithm, then we need to come up with a better way to encrypt messages and encrypt anything. So it's going to be a while, but we need to start looking at it and learn to counteract. So we saw this broad view. This is still a pretty zoomed out circuit diagram of Shor's algorithm last time. So it has some qubits that you want to put into an oracle, and you make them into superposition, and you entangle all of the qubits, and then feed it through the quantum Fourier transform to obtain a periodicity of a set of states. And that is a key number that will be used in basically once you factorize the number, you get this periodicity R. And I briefly mentioned that this quantum Fourier transform works just as any Fourier transform. And we have this actual physics experiment that is actually demonstrating Fourier transform using a grating, that if you shine a lot of electron beams through a slit, a grating with many slits, then this is a periodic grating. But if you don't know the periodicity, you can infer that from the interference pattern that you observe. And that's the basic idea of quantum Fourier transform. So I know for people just joining the class, it might just sound like too much already. You can go back to the previous class, which we spent less than 30 minutes on, going through some of these ideas here. And we're going to continue, and we're going to zoom into these boxes to look at actually how this whole Shor's algorithm is set up. But we wouldn't be using too much math. I'm using these graphics to guide people. Okay, so last time people asked me how many qubits would be needed to do the Shor's algorithm. So I was saying that, well, I heard different ideas that could vary, that some people said thousands of qubits, some people said millions and tens of millions of qubits. So how do you even check this? Just let's take a real RSA number as an example. And on Wikipedia, you can actually find a list of broken RSA numbers. And the simplest one, the smallest one, is this RSA 100 with 100 decimal digits. So this is a real number that was used before it was broken and is this long. So is a number that's a multiplication of two prime numbers, P and Q, and that's the two numbers that you want to know. And people broke it and found out that these are the two numbers that's used to make the N. And in reality, P and Q will be randomly generated. So random number generators are, oh, somebody's asking, Hans is asking, no presentation slides. Do people see it? I think so, right? Do people see the slides? Yeah, okay. Some people are not seeing it. That's weird. Most people do, so it might be on your side. So please check. Maybe you have to close Teams and come back. Yeah, thanks for the confirmation, everyone. Okay, so then these in reality, P and Q will be some randomly generated numbers. And you want it to be really large, and then you can make up the N, so no one would know the original P and Q are. But for this actual number N, here are the answers. And if we want to calculate how many qubits that's needed to run the Shor's algorithm to break this N, I quickly did a calculation based on this rule here. So if you want to encode number of qubits to represent your input qubits, then you need to have 2 to the number of qubits larger than n squared, and that gives us 659. And then you also need some output qubits that you need to have 2 to the number of qubits larger than n minus 1. So then that's 329. In total is about 1,000. But then this is not even considering any error correction. And this is the simplest, probably the shortest N, smallest N that's in the list. So for larger numbers, of course, you will need more qubits, but we're not even talking about having additional qubits to correct the errors that could be generated in your setup. So that's why there are larger numbers, and there are orders of magnitude larger numbers of qubits needed theoretically to run an effective Shor's algorithm. So that's how you can think about this, how many qubits we'll need. And then, of course, you need to entangle them. So you may need additional qubits to also act for that. So just rule of thumb, that's a really large number. So it will be hard to go through the algorithm with such a big number. So let's use a much smaller number to look at how this whole setup works. Let's take n equals to 35. It's a number that we know what P and Q would be, but just imagine that this n is unknown. And you can calculate how many qubits will be needed. And that's 2 to the 11, which is 2048, and that is larger than this number. So you will need that to encode. And then you can do a table truth table that shows you I have this X, and then what is the possible outcome if I have a guess. 3 here. 3 is a guess number. You can use any number here, but let's just say that we used 3. Then if you divide 35 by 3 to the power of x, you get a remainder. In the zero case, that will be 1, and then next one will be 3 and 9, 27. But then if you run the table down, you start to see some patterns showing up. So more than 12. Sorry, I think I just misspoke about this being the number of qubits, but 11 is the number of qubits, sorry. But this is the number of states. So then you will have this much number of possible x values, and then you start to see it has these repeated remainders showing up. So every 12th time, you will get this repeat. So 1 will repeat every 12th time, 3 will repeat every 12th time. Start to see some patterns here. But again, 35 is a very small number, so we can draw a table like this. But then if it's a really large number, we can't really do this. So 2048 states will be the smallest number. 11 will be the smallest number of qubits that you need to cover this number here. And then you see this periodicity starting to show with 12. So that I just also already mentioned that 8 to the power of 0 mod n, 8 is 3, and then 3 to the power of 12 mod 35, they all equal to 1. So these are all these numbers, they're all 1s. Then you can see that if your remainder is 1, then a to the power of r minus 1 should be divisible by n. Or you can use another number 3 to the power of 1 minus 3 should be divisible by n. But here you start to see that r, because r is the periodicity, and that minus 1 should be the smallest number that is divisible by n. Then you can rearrange it. This is all pure math and some clever trick that has nothing to do with quantum. And that's how you can, even if you want to classically do this, you will go through this step. So if you want to figure out what is divisible by n, you would then do some rearrangements. So there's no reason we can't make r divide by 2 and then time the 2 back. And then because you can write it this way, you can split it into 2 terms like this. And then your r needs to be even because you have to divide it by 2. So, and also these 2 terms cannot be individually divisible by n because we already know a to the r minus 1 will be the smallest number that is divisible by n. So this one cannot be independently divisible by n. Therefore, this one cannot be independently divisible by n. Then you start to see, okay, if the n can be written by can be divisible by 2 terms, then an n can be a multiplication of p and q. Then we can infer p can be divided by this term here, and just doing a calculation, you know the number, and q will be divided by this, and you'll get another number. So what this would be is just a clever trick that in order to get p and q, you just need to have the grand common divider of this term and n itself. So if you do that, the greatest common divider. For p, you could get a 7, and q, it will be 5, and then 5 times 7 is exactly 35. So that is kind of a reversible way to arrive to this stage by looking at the periodicity in this table. But if you want to look up for a different type of proof, the video that I recommended last week also has another proof to show that you can do this. So far, nothing is quantum. And to get to this point, 5 and 7, you are doing this greatest common divider. And this can be solved. How do you do this, or do this in general? This can already be solved by the Euclidean algorithm that's being invented thousands of years ago, and it's being used all the time. And you can easily find algorithms that can do this. So it is totally run by classical algorithm. And the pattern you will see is that if you keep subtracting the larger number here by the one you want to get, you would find numbers that are also divisible by the same common denominator. So that's how you can eventually get to a very small number that you would know is divisible by 7. So all of these are commonly used, commonly done. But then the hardest step is really finding the period R for a large n. We see from this table with a small number, 12 is the answer, but then if n is super big, then there's no way you can really classically do that. That's then how quantum computing come into rescue, or mess it up by introducing this very efficient way to get the periodicity R. And this is how, again, that circuit would look, and it basically comes into 3 parts. The first step is doing some superposition, as you have seen in all of these algorithms, quantum algorithms, that we want to put something into an entanglement. So you do a H-Hadamard gate to all of your input qubits, and then somehow in here you can entangle them. So let's take a look what's happening with the aid of some graphics. You have, say, quite a few qubits coming in, and each of them has a number encoded in them. And you can imagine them as all these amplitudes for your waves, and they're different numbers. So you basically encode all of these numbers into these amplitudes. And then inside this box here, these are the oracles that we have seen previously that has some kind of control based on the input qubits. So what this does is really to put everything into superposition in entanglement. You can imagine that in here, the amplitudes, the wave would look something like this. So all of these in superposition and with all of the other ones in superposition, and you start to have these patterns, just like this table here. So all of these are the peaks, and then again, it's showing the same set of peaks. Again, it's showing some set of peaks. The periodicity is R. So they're all the same. So this one is the same as this one, except there is a phase difference. There's a phase shift. So when you have a periodic state that is f of x equals to f of x plus r, with r being this pitch here, that just says that if you shift it by amount r, you will get exactly the same wave there. And the only difference between them is this phase factor. And you can see that you can actually prove this f of x equals to f of x plus r to be something with these phase shifts and their own amplitudes. So then you can write out all of these repeated units, and this number n here is just a integer number. So in our case here is just basically a mathematical representation of this set of wave functions here. So 0 and 1 are not our 2 levels, 0 and 1, but is the x 0, 1, 2, 3, 4, 5. up until this Q is the very last number. So I didn't introduce the notation, but don't worry about it. It's just the last number here. So if you want to just write out rigorously what comes out of them, you will see that they will have all these phase vectors. This picture is from the book from Nelson and Tron, which I recommend you go to. I think with the knowledge that you have accumulated following this class, which is kind of a bridge between 0 to this book. So then I think now this book might be quite useful for you to continue your studying, and is a very good reference book. Also, this GitHub project is a university students project. They wrote a algorithm based on Shor's algorithm. They represent it in code, so they're also using this picture here. So just some references for you. Don't worry about too much detail, but then let's see what's next. If you then measure this here, measure these output qubits, you don't have to do this. But if you do, then you will obtain things like basically it would pick out one of the possible outcomes. You could get a 1. You could, but then if it's 1, then there are multiple contributors. X could be 0, could be 12, could be 24. So you will get these peaks with that single amplitude left out, but it's still a periodic wave function. So that just says if you measure it, all of the other possibilities might be canceled out because of the measurement. And what you're left with is one of them, but it doesn't really change here. You don't have to do the measurement. If you do, then you would feed this wave function into the quantum Fourier transform. If you don't do that, you will feed all of these ones into the quantum Fourier transform. But either way, what you're gonna get is the number R, the still periodic. So the next step is to find R. As I showed earlier, is like a grating with the R unknown, but then afterwards, you know that the interference pattern, you will get an interference pattern, and you would know that the pitch between them is proportional to 1/R. So what this part of circuit for Shor's algorithm is really to arrange your numbers into a way that you can feed into quantum Fourier transform. You're basically letting all of these possibilities be in superposition and feed all of that into this box here. And then the quantum Fourier transform would just transfer from a R space to a 1/R space. That's pretty neat. Of course, with a lot of numbers, is a complex circuit to set up. But you can take a look at like a 3-qubit example. H is the hardwired, but then you start to have this control between different qubits. And S gate, remember, we learned about this earlier, and there's the T gate. If you don't remember what they are, look up on a previous single gate class, but they give you this phase. So an integer number of pi/8 for your gate. So if you want to write out what this quantum Fourier transform matrix looks like, with 3 qubits, you will get this matrix. So you can imagine with a lot more numbers, you will get all these subdivision of phases, and they have some periodic patterns inside the matrix itself. And this is again taken from Nelson and Tron, is a good example in the book. If you want to look at a larger number, so basically that's how it's done, is you have these gates that are subdivisions of these separations. And the logic, if you just turn this graphic into this mathematical representation. You start with some zero state, and then you put them in superposition using the H gates, and then apply the oracle, which put everything into this periodic arrangement with this phase difference. So then you start to see this 2 pi L in their case is our n here, an integer. So pi x over r. And then this you already see is our very important factor that has the r in it. If you do a Fourier transform of that, even if you don't think about quantum Fourier transform, just normal Fourier transform, you will get something, some other function that is proportional to 1 over r. And then that's how you can then be allowed to directly obtain r. It's really cool that for me, I imagine this like in a physical system, like in the periodic lattice of a solid state. You have all these atoms in a periodic arrangement, and then you can shine light on it, and all these periodic atoms scatter your light, and then you will get a interference pattern of the light on this side. By looking at how these patterns are arranged, and they're also periodic, you can figure out how your actual material lattice periodicity is. So thinking about this is exactly the same. This is just a mathematical representation of doing a scattering experiment. So that's basically what Shor's algorithm does. If you just look at each step, it's actually not that complicated. And another way to think about this here is, say this is QFT, and there's a swing. If you're pushing it at the same frequency as the swing, you will have these amplified, you will have the amplitude in sync. But then if you are out of sync, if you're pushing it at a different frequency from the spring, from your daily experience, it will gradually, the amplitude will cancel out. So what this QFT is doing is that is canceling out all the other ones, but the one that is the correct periodicity. So that's another way to think about it. So we don't have much time to actually do a exercise, but we do have a sample. There are not a lot of Shor's algorithm code out there, but luckily we have one using QSharp. So on the GitHub Microsoft/Quantum, you'll be able to find our samples. And I actually have it open here. I would highly recommend that you go download it. I think walking through this in class is actually not as good as just looking at it yourself, because it's also, you need some time to look through all of these, and luckily it's all very well annotated. So I will highly recommend that you clone the samples GitHub repo and try to look at the Shor's algorithm at your own pace. So that's it for today. The interesting about Shor's algorithm is also you'll be able to learn about some libraries, API libraries, and the numeric library that's available in QSharp. Like you would need the arithmetic library to arrange your data in a certain configuration. The quantum Fourier transform is captured in the Canon library. So take a look at the sample and look at these libraries. I'm sure that would be beneficial. So any questions I can try to answer here, and I can stay for a couple minutes. But if at any point you have questions about quantum computing or anything related to quantum computing, you can post in Hackaday project page. All the recordings, including this one and the slides, are on there, but you can also look at the recordings on YouTube. And as we discussed last time, next Sunday, we're going to do a Q&A on career in quantum computing. I think this group wants to probably have some people interested in joining quantum in their full time or doing projects in quantum. And I can give some ideas of what types of jobs are there and what types of skills are needed in quantum computing and things like that. So we're gonna do a light class next week. Great, thanks everyone.